welcome to NPTEL course on power system protection. We are going with transformer protection, differential relaying principle. In today's lecture, we will discuss on different steps before the processing by the differential relaying. In the process, we will go for this vector group adaptation, the current normalizations. These things we have already addressed in the last lecture, but how those things are being processed, that we will learn today, and at the end we will have, we can say that, examples on external and internal faults in a transformer and how the differential relay performs during that time, that we like to see. Now, in the last lectures we have seen that differential relay is a promising technique for transformer protection, but it needs proper processing of the current like the normalization aspect before the corresponding differential of high voltage winding side current and the corresponding low voltage side winding current are being analyzed. Now, that happens to be phase to phase basis for each of the phase, and any of the comparison, if the corresponding differential current or the operating current, as we mentioned, becomes significantly high and it falls above this, you can say that these characteristics, then it becomes a trip decision. Otherwise, we assume that the corresponding state, corresponding situation is a normal operation condition and the relay does not allow for any trip decision, it remains silent. We know, you can say that, how to normalize the current using the current, the CT ratio of one side or the two side, that is high voltage or the low voltage side. You remember the one, you can say that, side we consider for the high voltage and two for the low voltage in our convention. But before going to this, the differential calculation, for the assessment of the assessment by the relay on trip or restraint. So, this, for that two more steps are required, important steps. One is, you can say that the zero sequence elimination. So, we will see, you can say that why that is required, but that is most essential when you can say that the site of the transformer where it is star grounded, where the zero sequence current is expected to flow. There is another one, you can say that important step, that is vector group. In last class we discussed that for different vector group connection of the transformers, there is phase shift angle between the high voltage side to the low voltage side. In that case, you can say that we need essentially to process the corresponding current, particularly low voltage side, so that the phase, you can say that, displacement can be compensated. So, that you can say that these two, you can say that, important steps are the important steps that are to be processed before the final comparison is to be accomplished in a differential relay principle. We will learn each step in details. In overall, the differential processing, the differential current processing, the corresponding characteristic which we have talked about here for calculating the operating current and the restraining current, and to make a judgment whether the operating current is higher than the, you can say that, in higher level, you can say that above the, you can say that, the corresponding characteristics or not. This judgment, you can say that, is obtained through different steps of the processing of the currents available from the CT. Now, let us, you can say that the winding one refer to the high voltage side, CTs are there, the digital relay acquires the corresponding sample does the normalization, which we have learned in the last class about that calculation of the normalized current. So, that goes, you can say that from the CT secondary current, capital C here refers to the high voltage side, and so we have this ABC 3 phases. The corresponding currents after the normalization are IAN, IBN, ICN after the normalization. Then as already mentioned, if it is a star grounded system also, we require zero sequence, you can say that elimination, subtraction of the zero sequence current from each of the phase current, and then we get, you can say that IAZ, IBZ and ICZ. The Z here you can say that refers to the zero sequence elimination perspective. So, this is, you can say that the processing from the high voltage side. Now, come to the low voltage side, winding 2 side. So, we have the CT2 corresponding signals are available to the relay here, and then you can say that it goes for this normalization, and in the normalization you can say that we have the ICN, IBN, IEN available in the low voltage side, and then zero sequence eliminations if it is required, and so then you can say that the IAZ, IBZ, ICZ phase currents are available after the zero sequence elimination, and then you can say that in the low voltage side we have a vector group adaptation. This is essentially required for the phase shifting that is being observed, you can say that due to the vector group. We will have, you can say that more discussion on each of these steps, you can say that for the processing of the relay, and then you can say that finally from the high voltage side and low voltage side the corresponding, you can say that currents are available, and that you can say that is being processed for the differential current and the restraining current, and to you can say that see whether it is a trip decision or no trip decision. So, we see, you can say that 4 important steps are there in this process of, you can say that calculating the differential current. First stage is normalization, then the zero sequence elimination, vector group adaptation in one side. In our the method which we are following is only carried out in the low voltage side. There are, you can say that methods available in other literature, other manufacturers, you can say that different manufacturers they carry out this vector group adaptation in different ways also, that you can say that the different ways, but that you can say that its only purpose is to compensate the corresponding angle with respect to the high voltage for the low voltage currents. Fourth step is decision applying differential principle, that is what you can say that the final step where the corresponding the trip or no trip decision is being carried out. Now, we see here that in the first step is the normalization current that we have learned in the last lecture. So, in this case we find the corresponding rated current from the MVA rating of the transformer and the corresponding voltage. If we take into account the corresponding current voltage, then this rated current you can say that is also in adjustment with the step changing position of the transformer also, and then you can say that similarly calculate for the rated current for this one using the corresponding current voltage, current actual voltage of the system from that one, and we can calculate the corresponding rated, you can say that current on the system also from the KVA rating of the transformer. If the that we can say that depends on the rating of winding 1 and winding 2 and so. Now, we see, you can say that the normalization is obtained as already observed in the last lecture about the CT ratio 1 upon, you can say that the rated current of that first winding, that is high voltage winding, into the corresponding secondary current in the available to here, you can say that in this perspective. Now, you can say that the I2 normalization for the second winding also is carried like that. If you have third winding, you can carry out like this for the third winding also. So, in general for the 3 phases, you can say that after the corresponding normalized, you can say that current can be available from the CT ratio for the high voltage side upon I1 rated, and then you can say that we have the available currents from the CT secondary. And similarly, for the low voltage side also the normalized current can be available from the CT ratio 2 upon I2 rated, and then you can say that we have the 3 phase currents IA, IB, IC in the secondary side of the low voltage side. Second step is on I0 eliminations or 0 sequence eliminations. Let us first consider that, see why do we require this. Now, this is a, let us say a simple system, a transformer fed from an AC source, 3-phase transformer of course. This side is, let us say, consider delta, this is star, star grounded and so. So, we have CT this side and CT this side, agree, and then this is our consider differential relay which does the calculation for operating current, standing current and make a decision perspective energy. Now, for this system, for a fault you can say that external to the relay, if you see you can say that the corresponding sequence diagram becomes like this. So, this is the fault point. So, we have positive sequence diagram, negative sequence diagram and 0 sequence diagram. This side being delta. So, therefore, you can say that the corresponding for the delta you can say that star connection you can say that the corresponding transformer you can say that 0 sequence diagram becomes this for the transformer, and then you can say that we have like this. Now, in this case if you see, then the positive, negative and 0 sequence are connected in series, considering this to be a phase say that line to ground fault case, and then you can say that what you see here that the positive, negative and 0 sequence are connected in series, and if you see this path of flow of current. So, this path of flow of current like this and this, and then you can say that from this to this. So, it clearly says that these two CTs you can say that which are there to the left and right of the you can say that this delta side and the star side, in both the you can say that CTs positive sequence current flows, negative sequence current also flows, but if you see here you can say that the 0 sequence current flows only in the you can say that right hand side CT, that is star grounded side CT. No 0 sequence current flows in the can say that in the delta side, we have marked here star, to this you can say that here also star. So, the 0 sequence current does not flow in the star, and that we know you can say that from our power system analysis knowledge also, that this delta connection you can say that the 0 sequence current which flows in this side, that flows you can say that it becomes a circulating current inside the delta winding. It does not allow you can say that the current to flow in the line side of the delta you can say that delta winding connection. So, that is what you also can say that in agreement with this from the sequence component perspective also, which we have learned at the beginning of the lectures on power system protection. So, that implies that for this fault a 0 sequence component you can say that will be flowing in the star grounded side and will not flow you can say that in the delta side. So, that becomes an additional current you can say that which we are you can say that the corresponding CT sees in the CT you can sees in the delta and the star. So, that additional current must be subtracted before the comparison, otherwise corresponding comparison or differential current becomes erroneous one. So, that leads to the situation of 0 sequence current must be subtracted from the grounded terminal before applying differential principle to the transformer protection. Now, how to do this you can say that the 0 sequence eliminations. So, we know you can say that the 0 sequence current is 1/3 upon you can say that IA plus IB plus IC, both for high voltage you can say that side and also for the low voltage side. So, like that you can say that what you do that from the individual phase current we subtract the corresponding 0 sequence current. This is high voltage side. So, from each one you can say subtract the 0 sequence current, and then you can say that we get the consider that after that the corresponding IAZ, IBZ and ICZ. The Z here you can say that corresponds to that 0 after the 0 sequence elimination or subtraction from the phase current, each phase you can say that currents in the high voltage side. So, if you put you can say that these to be considered in a matrix form, then it becomes equals to IA, IB, IZ you can see becomes 1/3 of you can say that this, because we know here this I0 you can say that is 1/3 of IA plus IB plus IC. So, this becomes a matrix form you can say that the relay can calculate the corresponding after the 0 sequence current, the corresponding values of phase A, phase B, phase C current in the high voltage side. Similarly, in the low voltage side also applying the same you can say that matrix you can say that calculation method from the you can say that phase currents of the low voltage side, we can get the corresponding you can say that the corresponding 0 sequence the currents you can say that following the 0 sequence elimination. Then the next step, important step is step 3 is vector group adaptation. In the last lecture, as I already mentioned, we talk about there is a phase shift due to the different vector groups, and we say that we take the corresponding reference as the high voltage winding, and with respect to this corresponding low voltage winding, the corresponding current legs you can say that by the corresponding the vector group, you can say that depending upon the vector group. The vector group matching means that the low voltage side currents are rotated with respect to the high voltage side currents in accordance with the vector group of the transformer to be protected, thereby phase coincidence with the high voltage side current is obtained. So, the sole purpose as already mentioned, and which you have seen, you can say that in our earlier lecture also, that suppose you have a YD1 connections where k becomes equals to 1, and we see that the corresponding for our CT connections such that in the last lecture we have seen that the low voltage you can say that current lags the corresponding high voltage you can say that current of the same phase by an angle of 30 degree. So, to have you can say that proper comparison, they must be aligned you can say that 2 in 1 you can say that way, and that is the reason you can say that with respect to considering the high voltage as the reference, the corresponding low voltage must be shifted by this 30 degree, and that is what you can say that you say that the phase coincidence has to be you can say that done before you can say that the corresponding differential principle is to be applied. So, in general what we say that we consider the voltage the high voltage winding to be the reference, the low voltage winding lags in accordance with the vector group number k, and this you can say that how much angle k into 30 the corresponding the vector group it is k, it means that k into 30 degree, by that angle the corresponding low voltage you can say that of that phase will be lagging to the high voltage current. The vector adaptation is applied in the low voltage winding only, and this is you can say that, and the adaptation can be determined directly from the connection of the winding. So, we require only information of the k, that is the vector group you can say that number only. So, now the point you can say that this is the philosophy we will follow in our you can say that approach, but as already mentioned different manufacturers you can say that go for different calculation way to get the corresponding phase coincidence from for the two you can say that winding sides high voltage to low voltage. Now, for this you can say that vector group adaptation, how that is being done, we have you can say that take a matrix form like this we did you can say that we see for the zero sequence elimination also. So, what we did is let us you can say that in this case the vector group adaptation is accomplished, we are accomplishing the low voltage side. So, this IAV, IBV and ICV, this is after the consider the corresponding vector group adaptation, and from what the corresponding IAZ, IBZ, ICZ, that is after the zero sequence elimination. So, from this current we are going to this current using this you can say that the transformation matrix, and in this transformation matrix 2/3 of you can say that cos k 30, k stands for you can say that the group number, the vector group number. Suppose we say have this transformer is YD 5, it implies k equals to 5, if the transformer is YD 1, k equals to 1 and so. And then you can say that cos k plus 4 30 degree, suppose it is 1 means this is cos 30, 1 plus 4 is 5. So, 5 into 30 is 150, that is shifted by 120 degree, k minus 4. So, then this becomes equals to 1 minus 4 is minus you can say that 3, minus 3 minus 30 consider becomes minus 90. So, that is what you can say that again you can say that we are talking about in terms of that, and then you multiply that. So, this again you can say that the matrix you can say that if you see then this k minus 4 30 this term comes here, k 30 here, and then k plus 4 30 and k plus 4 30, k minus 4 30 and k 30 degree comes out to be this. Now, this sole purpose you can say that is that to orient the corresponding IAB IC with respect to that to the high voltage winding, and that you can say that vector group adaptation you can say that things we obtain from this one. So, now you can say that this matrix comes from you can say that the perspective of using that we know from our you can say that the fault analysis using sequence component, positive sequence you can say that positive sequence voltage or current in you can say that in terms of you can say that this that it leads by you can say that angle of 30 degree you can say that the j theta to the consider the corresponding to the corresponding aspect of you can say that in the particular transformer you can say that YD1 and so, and then you can say that we also learn, you can say that in case of the corresponding negative sequence, that the corresponding, it happens to be reverse one, it happens to be a minus 30 degree or lagging, you can say that angle perspective and so. So, considering the positive sequence and negative sequence perspective, the corresponding e to the power j theta and e to the power minus j theta terms comes here, and using that you can say that the corresponding corresponding matrix comes out to be in terms of the cost terms which we are getting here. Now, we see now the final step is on decision with the differential principle. So, we already got, you can say that the vector gravitation and then CV, and from this side we have already zero sequence elimination perspective. This is low voltage side, this is high voltage side, and then you can say that the middle one is about the differential current is to be calculated, and the corresponding differential characteristic principle has to be applied. So, for that you can say that the I operating current in phase A, phase B and phase C are obtained, you can say that by the phasor addition of, you can say that the IAZ, IBZ, ICZ from the high voltage side and the corresponding IAB, IBB, ICB from the low voltage side. So, we have this addition, this depends upon as the principle we have already applied, depending upon the CT connection perspective and all these things. So, this operating current is applied to the differential relay in this percentage by differential relay characteristics, and there you can say that the relay sees, if it is greater than, you can say that this IPU, and if it is greater than, you can say that the M1 into the corresponding restraining current or M2 into the restraining current, then relay makes a trip decision, otherwise it remains in a restrained position. We will go to examples how the corresponding steps are being accomplished, and then you can say that how the differential relay can make a judgment whether the fault is external or internal. First, we have considered for an external fault, a G type fault in high voltage side. So, a simple system we have considered, a 33 kV source grid, and then we have, you can say that a transformer. The transformer is 220 kV to 33 kV, and then the transformer is YGD D1 and 50 MVA transformer, and we have, you can say that high voltage side capital ABC and low voltage side small ABC as you have already defined, and then the corresponding, you can say that steps are to be accomplished, you can say that from the CT secondary that will be processed by, you can say that the numerical relay platform. A 3-phase load is connected which is being fed from this source through this transformer. So, for an external fault of AG type in the high voltage side, the recorded data are pre-fault. This is normal loading condition that the becomes, you can say that IAS, IBS, ICS are the secondary current available through the CT secondary to the relay are having some little more than, you can say that 1 ampere current. This is the status of the loading condition. Then the low voltage side, you can say that CT secondary current in the pre-fault side is also similar, having greater than 1 ampere or so after the transformation, or you can say that through the 5 ampere CT and so fault. Now, the fault, you can say the data are like this. So, the fault is in phase A to ground, and you notice here you can say that the phase A current, you can say that becomes significantly high, 8.8 ampere with an angle of 1040, and the other two, you can say that phases are having negligible current as compared to the fault current, and they are almost in the normal state as you have seen the pre-fault. Now, in the low voltage side, which is the source side here, the primary side so called, then the corresponding current, you can say that it happens to be IAS equals to 6.35 and IBS equals to 5.76, ICS equals to 1.55. So, notice you can say that the two phases instead of one phase, you can say that current in the primary in the high voltage side, two currents are now increased. This is due to reason here. If you see here, you can say that the fault is in A phase. So, this current increases. So, now therefore, you can say that if you go to, you can say that to the low voltage side, the corresponding this winding corresponding winding in phase A, this current will has to be, can say that will be proportionate current flow, but this is connected to, can say that to the phase B winding like this. So, therefore, phase A and phase B winding the corresponding phase A and phase B, you can say that line side currents are being affected, and that is, you can say the reason we see, you can say that here high amount of current you can say that in phase A and phase B. Now, what we see here, next step we can say that we will go step by step 1. So, in first step we can say that we will see that the I rated, I1 rated high voltage side and I2 rated you can say the low voltage side, 50, 220 you can say root 3, that gives you 132, 131 ampere, 50 that is MVA, 33 kV into root 3 you can say that gives you can say that 875 ampere, the corresponding current and all these things. Based on that you can say that we select you can say that the CT ratio to be 1.25 times, and so as already we have learned from that, and the CT you can say that CTR R1 you can say that high voltage side becomes 200:5 with a ratio of 40, and the low voltage side with a ratio of 1100:5, 220 factor happens to be there. Now, we will consider go for the normalization perspective after the CT ratio has been frozen, and then you can say that high voltage side we got the corresponding normalized currents to be CTR1 upon I rated, and using the corresponding secondary current of the from the CT currents what we have got for the during the fault situation. We do not analyze the pre-fault situation here, the relay does for that case. So, therefore, you can say that we got the corresponding things to be considered 2.68, 0.37 and 0.3 you can say that 4. These are the considered the corresponding currents we are getting after the normalization. Similarly, in the low voltage side, after applying to this you can say that to the low voltage currents you can say that this side. So, we say you can say that here the CT1 ratio we got 1.6 and 1.45 for the phase A and phase B, which are having the higher currents, and that you can say that is after the normalization of these steps. So, this is first step about the normalized current you can say that both at high voltage level and the low voltage levels. Next step is on zero sequence elimination. So, straightforward we see here this you can say that transformer you can say that the high voltage is connected in star grounded. So, zero sequence current will flow in this side, no more you can say that zero sequence current will flow in this you can say that in the delta side perspective. Now, in that case you can say that we see that zero sequence current has to be subtracted. So, as already mentioned 1/3 of the matrix the zero sequence corresponding matrix, and then the normalized current is being multiplied with that, and then we got you can say that IAZ, IBZ and ICZ. So, after the normalized current is substituted here, we get the corresponding current after the zero sequence eliminations to be 1.72, 0.79 and 1.04 ampere in the high voltage side. Similarly, you can say that we can obtain for the low voltage side you can say that IAZ, IBZ and ICZ. In this case you can say that there is no zero sequence current in the delta side. So, you can get same as you can say that IAN, IBN and ICN, which are the normalized currents in low voltage side. Now, for this external fault we will go for the step 3, that is the vector group adaptation, the phase angle you can say that coincidence perspective and so. So, we have the consider the corresponding matrix k equals to 1 here because of this is a YD1 connection. So, substitute value of k, then you got the corresponding angles to be cos 30, cos 150, cos minus 90 and so, and then you can say that this rotating kind of thing. So, we got the corresponding IA voltage vector after the vector group adaptation, that becomes 2/3 of this matrix into the corresponding IAZ, IBZ, ICZ, which we have already calculated we reach up to this step. So, by substituting the corresponding values we got you can say that the corresponding current to we can say that equals to 1.75, 0.81 and 1.05. So, this is the can say that corresponding currents we are getting after the vector group adaptation. So, we have reached up to consider up to this step from the low voltage side. The fourth step you can say that is on the decision process you can say that the differential you can say that current calculation and the restraining current and then applying the corresponding trips. So, we got the corresponding I operating current in phase A, B and C. So, then you can say that we applied the corresponding positive you can say that IAZ, IBZ, ICZ plus IAB, IBB, ICB both these sides, and then we add these two currents you can say that phasor sum of these two currents, and we got the corresponding values to be 0.04, 0.02 and 0.02. It seems the corresponding values are pretty much smaller than the corresponding values from this side. So, if you see you can say that these you can say that values, this become you can say that the values seems to be smaller. Now, for you can say that the relay will decide based on the can say that the trip the percentage bias you can say that trip characteristics. Now, let us now calculate the I restraining current. The I restraining current you can say that k into IZ minus IAB for each phase you have to calculate. So, K you have taken is 0.5, that is the that the restraining current relations we have used. So, 0.5 into IAZ minus IAV, substitute these values of these phasor values, and then you got the value to be 1.73 ampere magnitude of this. M1 we have considered this part is 0.2 and M2 we have considered is 0.5. So, now IP is considered we have considered is 0.2 ampere, this is normalized current. Now, what we see you can say that let us say phase A current is the I operating A comes out to be considered 0.04 ampere, magnitude part only we consider in this for this consider characteristic relations. So, this 0.04 ampere is you can say that less than the corresponding IPU threshold value. So, therefore, this is the first check you can say that which the relay does, and this corresponding you can say that I operating current phase A, which is highest here you can say that out of these three, that does not qualify this first test. So, therefore, the relay you can say that confirms that this is not at all you can say that a trip decision, it is a restrained or normal situation of the for the transformer. So, this confirms that you can say that this is an fault, maybe a fault, but this is external to the transformer, it has nothing to do with the transformer. Next case we will go for an internal fault case. So, same you can say that arrangement for the transformer, only you can say that the corresponding fault is created in between the two you can say that sensors, group of sensors CT, and we have created a fault you can say that internal to this arrangement. So, it is in zone fault in this case. For this case you can say that the prior pre-fault condition remaining same for these both high voltage and low voltage winding side. Now, the fault if you see you can say that phase A you can say that fault is created, phase A to ground fault is created. So, in this case the corresponding current from this side high voltage side, this current decreases substantially, because this is a load side, no source is there. So, therefore, you can say that the current flows from here to here, and this side you can say that the current flowing is very substantially lower now. The other two phases remains almost intact, and in the delta side you can say that because this phase current becomes larger due to this fault. So, therefore, you can say that the delta side you can say that phase A and phase B current become significantly high, as already explained in the external fault case also. Now, you can say that this fault current will apply the corresponding 4 steps you can say that for this you can say that differential link principle, normalizations, we apply the same you can say that principle like the CTR, CT ratio and the rated current. So, and they got the consider the normalized current using the CT ratio and all these things to be 1.6, 1.45 and 0.39. Zero sequence eliminations IAZ, IBZ and ICZ capital, and then a small IAZ, IBZ, ICZ, the way we did for the earlier case of external fault case, multiply this matrix you can see that and got the you can see that corresponding currents to be 0.09, 0.35, 0.33 for the high voltage side, and then the same you can see that is for the low voltage side, the IAN, IBN and ICN. Now, next step 3 is on the vector group adaptation. So, for k equals to 1, these you can say that matrix we have already seen for the external case, 2/3 upon you can say that root 3 by 2 and so, and then you can say that use the corresponding IAZ, IBZ and ICZ you can say that values and get the corresponding you can say that value to be 1.75, 0.81, 1.05 you can say that in the low voltage side IAB, IBB, ICB, but the B you can say that stands for you can say the vector group adaptation. So, we have reached up to you can say that these 3rd steps here which is being carried out in the low voltage side. Now, final step you can say that is on the decision making process. So, for the operating current you can say that for each phase of A, B and C you can say that we get the corresponding you can say that this plus this, and then you can say that we add these two current phasor you can say that currents and got the values of 1.84, 0.92, 0.92. Now, see here as compared to the external fault case like highest there was 0.04, here we are getting 1.84 compared to the values of you can say that different phase currents of this order. So, that shows that you can say that the corresponding current here is significant, particularly phase A you can say that case, and we have this fault is AG type fault for the transformer and it is in zone fault, internal fault to the transformer. So, for this case I operating you can say that is 1.84 for phase A, and then you can say that the restraining current 0.5 IZ minus IB that is being calculated comes out to 0.83 ampere, M1 is 0.2 and M2 is 0.5 like the earlier case, IP is 0.2 ampere you can say you have considered. Now, in this case the I operating current is greater than IPU. So, that is the first check, 1.84 is greater than you can say that 0.2. The I operating current is also you can say that 0.3 times you can say that M1 is 0.3 times you can say that of this 0.83, that gives you can say that 0.2 ampere. So, this I operating 1.84 is also greater than you can say that 0.2 ampere. So, that means that you can say that the corresponding point falls in the trip region, and therefore, it is ensured that this is an internal fall in this case. So, this you can say that the corresponding relay is able to detect the internal fall successfully, and for the earlier case you can say that of the external also it identified correctly. So, we see you can say that the differential relay essentially requires 4 steps, and the all 4 steps are important. The normalization of the current is has to be carried out. The zero sequence elimination to subtract the corresponding zero sequence current is also required, and then you can say that to have the consider corresponding phase shift carried out by consider different vector groups, that are to be considered also carried out by the vector group adaptation, and this we consider that in the method which we have followed here is being accomplished in the low voltage side. So, once you do this, you can say that prepare the corresponding currents, you can say that from the high voltage side and low voltage side, then we can make the corresponding comparison or the differential current, and at that time also we calculate the restraint current and apply the consider the percentage by differential characteristics to see whether the point lies above the consider trip characteristics or below. If it lies above, then it is an internal fall, otherwise it has the relay will go for a restraint operation. Thank you.